A very warm welcome, friends, to our new chapter, Understanding Cost Function and Gradient Descent. We will first understand cost function and gradient descent in the context of linear regression. Then we will proceed to logistic regression also. Friends, if you remember, when we did linear regression, we actually imported a module called linear regression, and that did the work for us, right? So we imported the linear regression module, then we called it like this: linreg is equal to linear regression. Then we fitted the data, linreg dot fit, and we fitted the training data to it, x train, y train. Then after the fitment was done, we predicted, right? Linreg dot predict, linreg dot predict, and we used the x test data for it. Then we measured our performance with R2 score and all that, right? We got numbers and we were happy about it, but we never asked the question here that how did the model get the best fit line, or how was the performance good? So here, through cost function and gradient descent, we are going to understand why this model performed well and how this model performs basically. So that has direct relation to cost function, loss function, gradient descent and all that. So we are going to understand this aspect in this class. So let me remove these. Let's say we have a simple linear regression in our hands. Let's say there is only one feature x, and it decides what is going to be the value of y, right? So this is how it happens. Now if you try to create an equation, basically the equation will look like this: a0 plus a1x is equal to predicted y, or y hat. This is going to be the equation of this simple linear regression. Now let us do one thing. We have the labeled data, that is the y values, and we have the x data also. Let's say there are total 1000 data. We have taken 800 data for training and 200 will be for testing. Now the actual values of y, let's say are distributed like this. It is distributed like this, friends, okay? Now, we are going to do linear regression on it, but we have a problem. The problem is, we cannot import any automated modules. We cannot import the linear regression module. We have to create the equation manually and then make it efficient, or create the best fit line manually. Now, how do we do that? Here comes the understanding. So let's say we have been told that we have to create the equation manually. So we have the x data and we have the y data, right? Now what we can do, friends, is assign the value of a0 and a1 a initial value and just start the equation. Let's see where it goes, right? We want to see where it goes. Now we initialize a0 and a1, and the equation becomes something like this: a0 plus a1x is equal to y hat, and for every value of x we have a y hat, and by combining all those we get a regression line. Now because this a0 and a1 we have just guesstimated it, it is obviously not the best fit line to begin with. Let's say in the beginning it looks something like this. Obviously you can see, friends, visually only this is not the best fit line, right? So there are errors, huge errors. What we do here, friends, is we try to measure the error, and our objective to get the best fit line is what? Is to minimize this error. Okay? So we have started at this very inefficient kind of a starting we have had. Now we are going to measure the errors. So there are, let's say there are m data points here. We are going to measure the error for each one. Y hat minus y. This is basically the difference for each and every point that we get. And what we do is, we do not stop here. We actually square it. Now this is basically the error squared. And for a single data point, this error squared is a measure of the loss function. Loss function is basically a measurement of error of a single data point. Now this is for data point 1. We do it for data point 2. We do it for data point 3. And we do it for all the data points. We do it for all the data points. Let's say we have 1000 data points. So we do it up till the 1000th data point. And each of these can be called loss function for that particular data point. But what we do is, we sum these up. This is called sum of squared errors. Now, to this sum of squared errors, we multiply one more factor. We multiply it with 1 by 2m. M here is number of data points. Right? This is a measurement which is called cost function. So loss function is a measurement of single data point error, and cost function is basically the average of all the data point errors. Now we have understood what is a loss function and what is a cost function, friends. Now, what is the objective of this? We have termed fancy things, but what is the goal of this? The goal is to minimize the cost function. To minimize the cost function implies to get the best fit line. Line of what? Best fit line of linear regression. So this is obviously, this orange line is obviously not the best fit line. We want to minimize the cost function, which ultimately will result in creating of the best fit line. So we have initialized the weights. Now how do we do that? The way to do that is through gradient descent. The way to do that is to ascertain gradient descent. Now what is gradient descent? To understand, before we understand gradient descent, friends, let us write the equation for cost function. The equation for cost function is given like this. J is equal to, J is the cost function. This is equal to 1 by 2m sum of y I hat minus y square. This is from 1 to m. This is the equation of the cost function. Our objective is to minimize this. And how do we minimize this? We said we use gradient descent. Now we try to understand what is gradient descent. So friends, we have this equation, right? Y hat is equal to a0 plus a1x. This is a simple linear regression that we are using. And y hat is basically a consequence of x, a1 and a0. X is data that we already have in our hands. So we can change a0 and a1 to get the best fit line. Now how do we do that? We will consider only a1 for simplicity's sake. So how we will change it? Let's see. We will change it like this. a1 is equal to a1 minus a factor called learning rate multiplied by partial differential of the cost function with respect to a1. This is how we are going to change a1, or for that matter any of the weights. The learning rate is basically a small number 0.1, 0.01 like that. How it impacts the gradient descent, we will obviously understand. And why it is called gradient descent, we will also understand that. Just bear with me. We are trying to make A1 more efficient, better fitting for the regression, and we are going to use this equation. How and why, we will understand step by step. So this is a small number, 0.1, 0.01. This is obviously the first derivative of j with respect to A1. Now what it comes to, let us try to understand. Del j del A1 is basically del A1 of 1 by 2m sum of y hat minus y, right? And this whole square. So if you actually differentiate it, this will come to, if you apply calculus to it, this will come to del j del A1 is equal to 2 by 2m sum of yi hat minus y multiplied by xi. This happens because of the differentiation of the equation, friends. So this 2 cancel out, and this becomes del j del A1 is equal to 1 by m sum of yi hat minus yi into xi. This is our equation, friends. This is our equation for del j del A1. Now when j is minimum, when j is at its minimum, that is, we are trying, our objective is what? Minimize the cost function. Goal is minimize j. Now when j is minimum, del j del A1 should be equal to 0. Now obviously we have a line which is very inefficient. We can go to the previous page. The line here is obviously not the best fit line, so j is not minimum here. So there is no question of del j del 1 being 0 here. So this is the non-zero number that we are dealing with. As we reach the minimum, this may reach closer and closer to 0, right? So that is basically our objective also. Now we know what del j del A1 calculation stands for. We can calculate it, right? We have our capabilities now. Learning rate we know. Previous A1 we know. Therefore we can create the new A1 and keep on changing it till the point j becomes minimum. Now let's say we are dealing with the first iteration of change. So the first change we are doing is this. We have initiated the weights, we have calculated del j del A1, we have assigned LR a value 0.1 say, we have assigned A1 also, and we use this equation to change it for the first time. So let's plot j with respect to A1. J with respect to A1. Let's say A1 is somewhere here, a low value, and j is here. Respective j is here. After this was the initial state. Now after this first calculation, after executing this equation for the first time, we have been able to reduce it just a little bit. It has come down here. Okay. Now we again calculate all the values. We again assign the new A1, right? A1, the new value of A1 that we have arrived at, which is somewhere here. It is somewhere here. So this A1, the new A1 we have, the LR we will keep it constant. Del j del A1 we calculate once again, and we execute this equation once again. Let's say it will come here. Like this, what we will find is this equation is taking the j downwards. But there is a catch here. It will come down only so much. After a point, we will again see that j is moving upwards. As it was coming downwards, it will again move upwards. But we will find a pattern of the curve, which I am showing here. The movement of j with respect to A1 will be a smooth bowl-like curve with one single point of minima. So herein comes two new terms that we have to learn. So this minimum point is called global minimum. And this bowl-like curve with a single minimum is called a convex curve. Now obviously if we have defined what is convex curve, we must also know what is a non-convex curve. A non-convex curve is something which does not have a single global minimum. It has multiple local minimums also. It can be like this, it can be like this, it can be something like this also. So these are multiple local minimas that are available, right? So this is basically a curve which is non-convex. Now we will come back to our equation. So initially what will happen is the j can be somewhere here. The j can be somewhere here, which simply means that a1 value is low and j is decreasing. So in that case, a1 will keep on increasing till a point j reaches the minimum and starts rising again. In a different case, it may so happen the initial j can be somewhere here, right? Somewhere here it can be. This means what? This means a1 is somewhere here and j is decreasing, but it will decrease with the decrease of a1. So a1 will keep on decreasing, j will keep on decreasing till the minimum point is reached and again the reversal happens. So the decrement of a1 has to be stopped. So we have seen two contrasting cases. One case can be j is high but a1 is low and we have to increase a1 slowly, step by step to minimize j. And in other case, j might be high and a1 also might be high. In that case, a1 will keep on reducing. Now, how do we ensure that these things happen automatically? Actually, these things happen automatically. Why do these things happen automatically, friends? This curve itself defines it. Here you see, if j is at some point here, the slope is positive, right? The slope is positive. Therefore, if the slope is positive, del j del a1, which is basically the slope, this is the slope, this will be positive. This will be positive. The impact of the entire expression LR into del j by del a1 will be negative because of the minus sign besides it. Because positive multiplied by a negative sign becomes negative. On the other hand, if j is somewhere here you can see the slope is negative, right? The slope is negative, this side. So this is a negative slope. This one is a positive slope. This is a negative slope. In that case, del j del a1 will also be negative. And if it is negative, what will happen, friends? This negative will become positive. This negative sign besides LR into del j del 1, this will become positive and a1 will increase. Now what will happen at minima, friends? At minima, if you draw a tangent here with the curve, it goes something like this. So if you try to draw an angle, the angle is actually 0. Del j del a1 is equal to, if you use trigonometry here, at the minima point, at j is equal to minima, is equal to tan of 0 degree, which is equal to 0. So this is again a geometric representation of the minimization condition. So we have understood what is gradient descent, friends. Gradient descent, why we are calling it gradient descent? We are going down a gradient especially when a1 is low. Also, if a1 is, we are going down some gradient to reach a minimum value. So that is why this process is called gradient descent. Now a note about the learning rate. The learning rate has to be sufficiently small but not too small that it takes too many iterations to reach the minimal point. But if it is too large, it may so happen that the A1 weights can go haywire. It can sometimes be here, sometimes go here, then again come back here, then again come back here. Like this, it may like bounce around. The J value may bounce around, and it may take a lot of time to reach the minimal point, if at all it reaches. So this has to be avoided. Too large number is not required. Yes, if you make it too small, like 0.00001, then it will take a huge amount of time and huge amount of your resources to actually reach the minimal point. So that also has to be avoided. We have to find an optimal number where these things happen at the quickest possible time. So friends, this is the equation. For del Z del A1 for a simple linear regression, right? What if it's a multiple linear regression? That is, there are multiple x variables. For that, we have to use linear algebra. And we are not going to derive it, but give you a certain amount of hint of how that will work. So cost function, minimization condition, and gradient descent in case of a multiple linear regression. So let's say we have an equation which is having couple of features. Okay, let's say we have an equation y hat is equal to a0 plus a1x1 plus a2x2. This is our multiple linear regression. In this case, how will the gradient descent look like? So instead of a curve, it will become like a three-dimensional bowl. Let me try to show it to you. So friends, as this gradient descent happens, and as this gradient descent happens, and as we so friends, as this gradient descent happens, and as we go on reducing the value of the cost function ultimately to the minimum, what happens to the actual regression line? Let us have a visual of that. So initially the line was like this. Now as the j keeps on reducing, we keep on getting better and better lines, friends. So let's say in the first iteration we get a line like this. Not that good, but an improvement obviously. Now in the next iteration we get something like this, let's say. This is happening as the j is reducing, friends. The j keeps on reducing like this or like this, and we keep on getting better and better lines. Now in the next iteration, let's say we get another even better line. And the j is going towards its minimum, right? Parallelly it is descending down the gradient. It is descending down this gradient. It is descending down this gradient as the lines keep on getting better and better. Now we reach back here. When it is at the minimum, we get the best fit line. So this is something like this. Okay friends, so this is the line we have when j has been successfully minimized. So this is how cost function, the gradient descent, the changing of the weights, and the linear regression line work together to create the best fit model for us. And this is all happening under the hood when we are just calling the models and applying them. Now this is for a simple linear regression. I want to give you a taste, an overview of how the multiple linear regression works, because when there are multiple features, the dimensionality increases and we have to use linear algebra for it. So we will not get into the derivations directly, but we'll try to get a taste of how it looks like. Let's say we have a multiple linear regression with two features. The equation of y hat is expressed like this. Y hat is equal to a0 plus a1 x1 plus a2 x2. Okay, this is our equation, friends. Now for this equation, how will the gradient descent look like? Instead of being a curve, two-dimensional curve, it will look like a bowl, friends. It will look something like this. You can see a1 is here, a2 is here, and this is how the curve looks like. So we still have a single global minima. The curve is still convex, but it becomes a three-dimensional bowl instead of a two-dimensional curve. Now as the number of features go on rising, we cannot represent in pictures, but the algorithms can still be able to minimize it. So we are going to apply the matrix format for linear regression with multiple features, or multiple linear regression. Now let's complicate things a little bit. Let's say we have a multiple linear regression with n features. Let's say y hat is equal to a0 plus a1 x1 plus a2 x2 plus dot 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 till an xn. There are n number of features, right? And there are m data points. There are n features and m data points. So this is basically y hat 1, x1 1, x2 1, xn 1. And these weights are obviously initialized randomly. They are not the most efficient weights. We have to do gradient descent and cost function minimization to make it the best fit line or the best fit equation. So we have initiated these weights, and in this condition, the data points look like this. y2 hat looks like this. a0 plus a1 x12 plus a2 x22 plus dot 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 an x n2 y3 hat looks something like this, a0 plus a1, because these weights, this is not even the first iteration of gradient descent has not yet happened. We are just writing the initial data position. This is a13 plus a2 x23 plus dot 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 plus an xn3. This goes up till m data points, right? ym hat is equal to a0 plus a1 x1m plus a2 x2m plus dot 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 an xnm. Now parallelly you have to remember, guys, we also have the actual values of y. We have y1, y2, y3 up till ym, right? Now for now we will ignore the actual y's. The only thing we are concerned about is this, that y hat, the weights and the features, how to equate them. So we can represent it like this: y1 hat, y2 hat, dot dot ym hat. This is equal to a0, a1, a2 up till an. That is from 0 to n. There are n plus 1 weights multiplied by the matrix of the features. So x11, x21 dot 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 xn1, x12, x22 dot 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 xn2. This comes down to x1m, x2m dot 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 xnm. But because of a0 there is a 1 also, a column of 1s also beside this, so we add that 1 1 dot 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 1. So this is basically the matrix form equation. Now we have to shorthand it. How do we shorthand it? Let's say we write a big y hat. A big y hat is equal to a big A into a big X. This is what we are talking about. Now once we have this, basically this is representing the first vector, A is representing the vector of the A's, and X is representing the matrix of the features. Now we try to find out the cost function from it. So we have this big y hat is equal to A into X, right? We have this. We also have the original y's, which is y1, y2 till ym. This is the original numbers. We represent it as y, a big y. Now from these two equations, how do we get the cost function, friends? The first thing that we have to do to get the cost function is to get the sum of squared errors. And we get that by multiplying the transpose of y minus ax with itself. So y minus ax multiplied by y minus ax transposed. This is what gives us the sum of squared errors. Now to get the cost function, all we need to do is divide this expression by 1 by m. 1 by m. This is our cost function, friends. Now to get minimization condition, obviously our goal is to achieve dj dA is equal to 0. This is our goal, right? Minimization condition for linear regression. For that we have to first differentiate it, get an expression and equate it to 0, and try to derive what happens out of it. So let us first differentiate it with del A, right? So del, let's do it in the next step. Del A of j is equal to del A of this entire expression, friends. 1 by m, we put a second bracket this time. Y minus ax transposed multiplied by y minus ax. This is what we have. Now we take the constant 1 by m out, and if you are acquainted with calculus, you would know, friends, that del A of a product is basically keeping one constant, we differentiate the other and then sum the expression. How? Let's do it. First, in the first expression, let's say this is constant. So this becomes y minus ax constant differentiated with respect to y minus ax transposed. This is the first expression, right? And the second expression will be plus y minus ax transposed taken as constant differentiated y minus ax. Now we have to simplify this equation. This becomes 1 by m y minus ax into minus of x, because this one cancels to 0 and this one becomes 1. So this only x remains and its sign remains. If you are acquainted with calculus, you would know what I am talking about. Otherwise, no worries, we can go into the expressions directly. You can skip this portion also. Plus y minus ax transpose del of this will mean minus x. Okay. Now this transpires to minus yx transposed plus ax x transposed plus, this becomes minus y transposed x minus y transposed x plus a x transposed, which means this expression reduces to 1 by m minus 2 into y into x transposed plus ax 2 into ax x transposed, because these two are the same expressions, right? Now remember the minimization condition, friends. For minimization condition is del j del a is equal to 0. So this expression has to be equal to 0 for the cost function to be minimum. So which means m is not 0, therefore minus 2yx transposed plus 2ax into x transposed, this has to be equal to 0. This implies, if you rearrange it, this becomes a has to be equal to y x transposed by x transposed. This is our minimization condition for the matrix form or multiple linear regression. The activity is happening in the same way. If you imagine it in the two-dimensional way, the same thing is happening. The only thing is you cannot imagine it in the dimensionality that the numbers or the features may happen. But if you reduce the things into 2-dimension or 3-dimension, you can actually picturize how the things are happening. The same thing is happening as it is happening in a simple linear regression. Only thing is dimensionality is in a range where your 3D imagination has no work to do. Only mathematics can do it. So now what we'll do is, we are through with the cost function concept for linear regression. Now we will move into the cost function concept of logistic regression. That is also going to be very interesting, friends. Cost function in the context of logistic regression. So friends, we all know that we use this equation for logistic regression, right? Yz is equal to 1 by 1 plus e to the power minus z. Now here z is nothing but the linear regression equation type only. Z is equal to a0 plus a1 x1 plus a2 x2 dot like this. So can we use our linear regression cost function only to do gradient descent here, or to minimize the cost function here? So the linear regression cost function looks like this: 1 by 2m sum of squared errors. We could use this equation, but the problem is the gradient descent becomes troublesome. Using this function, the convexity of the gradient curve is lost. It becomes like this. So the convexity, the smooth convergence to a single global minima is no more there. We have to deal with multiple local minima if we are going to use this kind of an equation. Right. So this becomes several combination of local minima. And our learning, like our gradient descent equation, can become confused very easily and think one of the local minima to be a global minima. Let's say this is a local minima. We do not want, obviously, for the cost function to stop at this value, because it is very high. J is this one, so it is a very high value. It can come down till here. So why stop here? So we have to do something about the equation, create a new equation or modify equation or do something so that this convexity is restored. How do we do that? We use a different kind of an equation. So what we do is, we use this equation. J or cost function is equal to minus 1 by m sum of natural log of y hat. This is the modification we do. But there is a problem, friends, with this. Basically, y hat here is a binary number. Y hat means the probability of y coming 1. Which means 1 minus y hat is the probability of y coming 0. Now here, in this equation, only the probability of y coming 1 is covered. So y hat has the tendency to go towards two directions, 1 and 0. This is covering only one direction, where it goes towards 1, or the probability of it going towards 1. So this equation is valid only for one condition, that is y is equal to 1. When y is equal to 1, this equation is valid. What happens if y is equal to 0? Obviously, we need a modification to this further. So this will be 1 by m sum of probability of 0, 1 minus y hat, natural log of 1 minus y hat. This is basically the cost function when y is equal to 0. Similarly, you can say we have some data. For a single data point, the loss function is given like this: minus ln y hat when y is equal to 1 and minus natural log of 1 minus y hat when y is equal to 0. So this is for a single data point, loss function, and this is taking the average of all the data points and is called cost function. Now when we use these equations, there is another problem. The problem is, now we have two equations for two conditions. We cannot work with it. We obviously have to reduce it to one equation. So those who derived these mathematics obviously found an ingenious way to convert these two equations into one equation also. So what they did was very unique. Let's say what they did was this loss function is equal to minus, you take minus common, y into natural log of y hat plus 1 minus y into natural log of 1 minus y hat. This is what they did. And for the cost function, minus 1 by m, because you are taking the average of the sum of y into y hat, natural log of y hat plus sum of 1 minus y into natural log of 1 minus y hat. This is what they did with the loss function and the cost function. Now we have found the cost function. Our goal is what? Minimizing the cost function. So let's get into it. Let's say our z is a simple equation, a0 plus a1x. We will ignore a0 for a while. The minimization condition becomes del j of del a1 should be equal to 0. This is our minimization condition, friends, right? Now this leads to a very interesting situation, friends. When we differentiate del j via del a1, the expression that we get is exactly the same that we get in the linear regression. Let us try to derive that form through differentiation. For those who have interest in calculus can go through this part. It's going to be very interesting how the derivation happens through the application of calculus. No, we'll remain in the same page. So let's say del a1 of j is equal to, we take the constant out 1 by m, del a1 of sum of y ln y hat plus del a1 of sum of 1 minus y ln 1 minus y hat. This is the ultimate expression, friends. Now we can further simplify this. This means sum of y del a1 y hat plus sum of ln y hat into del y del a1, because when you are doing, say, let's say del x of, let's say, pq, the expression goes like this. This becomes del p del x into q plus del q del x into p. This is basically how the expression goes, and we have used the same format here also. We have kept one constant and differentiating the other alternatively. In the second expression also we'll do the same thing. So this is plus sum of 1 minus y del a1 of ln 1 minus y hat. Let's write it below here. Here the space is not there. So we will be doing the same with the second expression also. Sum of 1 minus y into del a1 of ln 1 minus y hat plus sum of ln 1 minus y hat del 1 minus y del a1. This is the total expression, friends. Now we simplify it further. So before we go further, friends, we must know that two of the expressions here converge to 0 or become 0. First is this one, del y del a1, this becomes 0, so the entire expression becomes 0. So this becomes 0. Also, del 1 minus y del a1, this also becomes 0. So we are left with only two factors, this one and this one. So before we further try to simplify this one, we have to do something with the y hat. What we'll do, let's see. So y hat is equal to 1 by 1 plus e to the power minus z. If you rearrange it, this becomes e to the power z by 1 plus e to the power z. Okay, this is how it becomes. So we use this expression here. And also 1 minus y hat is equal to 1 by 1 plus e to the power z. So this is one expression and this is one expression. We are going to use these two expressions for further derivations. So we put in the values here. Minus 1 by m sum of y into del a1 ln e to the power z by 1 plus e to the power z. Although within first bracket I am putting the third bracket, it's not appropriate, but let's go ahead with it. Plus sum of the second expression we can ignore, 1 minus y ln 1 minus y hat is 1 by 1 plus e to the power z. So this is actually equal to del a1 ln ln 1 by 1 plus e to the power z. This is how it is. Now, log of a by b is basically log of a minus log of b. Log of a by b, even natural log, this is equal to log of a minus log of b. So we can use this for this also and for this also. Let's do that. Minus 1 by m sum of y into del a1 log of natural log of e to the power z minus natural log of 1 plus e to the power z. Right? This is what is coming to. Plus sum of 1 minus y del a1 of natural log of 1 minus natural log of 1 plus e to the power z. This is what it's coming to, right? Now we can simplify it even further. Minus 1 by m. Just to remind you so that you do not get lost, our objective is to minimize this, and under minimization condition this holds. So we are trying to find an expression for del j del a1 here, and we are claiming that it's going to be very similar to the one that we found in our linear regression problem. So we are trying to derive that. So this is y into, now natural log of e is basically 1, and this z becomes a coefficient of natural log of e. So this becomes del z del a1 minus sum of y into del a1 of log 1 minus 1 plus e to the power z. This is what it becomes. Plus 1 minus y. Log of 1 is 0, so this expression goes for a toss. This becomes del a1 of minus ln 1 plus e to the power z. Minus 1 by m. This one becomes x, because z is equal to a0 plus a1x, so this one becomes x. Sum of y into x minus, this one we do nothing about, sum of y del a1 ln 1 plus e to the power z plus minus del a1 of, because this is 1 plus 1 and this is minus 1, right? So this becomes minus ln 1 plus e to the power z. And this is a minus y, and minus this becomes plus. We write it here, plus sum of y into del a1 natural log of 1 plus e to the power z. And we close the parenthesis. Now you can see, friends, this expression and this expression are the same. So they cut each other. These two expressions cut each other. So we are left with only these two expressions. Right? Because these two have cut each other. So we are left with only these two expressions. So in the next step we'll write them. Minus 1 by m sum of y x minus del a1 of natural log 1 plus e to the power z. This becomes minus 1 by m sum of yx minus, first we differentiate 1 plus e to the power z, then we differentiate e to the power z, then z. So this becomes 1 by 1 plus e to the power z into e to the power z multiplied by x. How, friends? Let's see. Del a1 of ln 1 plus e to the power z. This is equal to del 1 plus e to the power z of ln 1 plus e to the power z multiplied by del a1 of 1 plus e to the power z. So this expression becomes 1 by e to the power z. 1 by 1 plus e to the power z. 1 by 1 plus e to the power z. This becomes. Okay. Now this is equal to del e to the power z of 1 plus e to the power z into del of e to the power z by del a1. Now this becomes equal to 1, because e to the power z differentiating, they become 1, and 1 is constant, so it becomes 0 when differentiated. So this is equal to 1 by 1 plus e to the power z into 1 into del e to the power z by del a1. Right. Now del e to the power z by del a1, this can be further simplified. We can mentally do it, friends. Once we are used to doing it, we can mentally do it actually. So z, this can be again decomposed further. This is like del e to the power z by del z multiplied by del z del a1. Now this one becomes e to the power z, because e to the power x del x is equal to e to the power x. So e to the power z by 1 plus e to the power z multiplied by del z del a1. Del z del a1 is z is equal to a0 plus a1x. So a0 cancels out because it's a constant. Then a1, because it's a1x, so a1 becomes 1 and x remains. So this becomes e to the power z by 1 plus e to the power z into x. This is how we get to this expression. So friends, if you have interest in calculus, this class will be interesting for you, this derivation part. Otherwise, the other parts are more useful to you, but I would insist, if you have been through calculus, please go through it. It's quite interesting. At least for me, it's quite interesting. So we closed the we forgot to close the parenthesis. Now we close it. Now one curious thing, friends, this e to the power z by 1 plus e to the power z part, this looks very similar, right? Okay, we also missed one more part. Here there is sum. So this is basically summation. So this is basically the sum. Now we find this expression very interesting, friends. Earlier we had derived that y hat is equal to 1 by 1 plus e to the power minus z. If you invert the 1 e to the power minus z to 1 by e to the power z and then transform it, it becomes e to the power z by 1 plus e to the power z. So this expression that we have is exactly like that. So this is y hat. So minus 1 by m sum of yx minus sum of y hat x. Now this is interesting, friends. We take the minus inside and this becomes y hat x minus yx. This transpires to 1 by m into sum of y hat minus y into x. Now we write del j del a1. This is exactly the equation that we had when we deduced the del j del a1 for our linear regression also, friends. So that's why we say that the culmination for both, or the expression that we receive for both after the derivation, is exactly similar. So this is the derivative equation or the differential equation for the cost function for logistic regression, which is exactly the same expression as the linear regression, my friends. So we stop here and we want to do one thing. We want to visualize how the gradient descent actually impacts our logistic regression practically. So let's draw the cost function curve first. So we have used the consolidated equation here. So there is no problem of convexity, right? So we are having this kind of a curve. Now let's say we have put certain weights in the logistic regression, right? A0, A1 we have put, and the ideal equation or the ideal curve should be something like this. Should be something like this, where this is the 1, this is the 0, and this is the curve, right? This is the ideal equation that we have when j is minimized, that is when j is here. But unfortunately, to begin with, j is not there, j is somewhere else. So we are getting this kind of an equation, let's say, or this kind of a curve, let's say. So it's pretty stretched out, right? we are getting this kind of a curve to begin with. So it's not a very good sign. So let's say J is somewhere here. So we are not getting a very good response through this. Now what we do is, we use this, we use the learning rate, so what we call the learning rate, and change the A1. Change the A1 means change it just like we did previously in our linear regression. A1 is equal to A1 minus learning rate into del J del A1. We know the value of this. Obviously, cost function is nowhere near 0. So del J del A1 will be a non-zero value. This will be a non-zero value. We can measure the value here. We know the learning rate. We have assigned it ourselves. So this is, let's say, 0.1 or 0.01 or whatever. We have set the weight A1. So this value we have derived, or the new A1 that we have, we can easily derive it. So after deriving it, let's say the value comes somewhere here. Okay, and the curve becomes a little better. Let's say it becomes like this. That's how it becomes. We keep on reiterating it. We keep on repeating this many times. Let's say 10 times, 20 times or whatever, using the learning rate. And we keep on getting lower and lower and lower. Ultimately, we find our minimal point. And at the minimal point, we have our ideal line. Right? We have our ideal line which overlaps with the best line possible. Nearly overlaps with the best line possible. So this is this one. And now we are happy. So at this point, we have arrived at it and we are quite happy to go ahead with it. So this is much about the cost function for logistic regression. We will also have a brief look at the matrix form for logistic regression or the binary logistic regression. Here we have specifically spoken about binary logistic regression. Please remember that. Let's say our z function is not that simple. It's quite complicated. Z is equal to W0. We are using, instead of A0s, we are using W0s. W0, W1 like that. W1 x1, W2 x2 plus dot 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 dot. Let's say there are n features, right? So this becomes the equation. Now we can write it as Z is equal to W is the matrix of these weights, W transpose into X. Once we have, let's say we have m data points or n number of data points, this becomes the matrix, because we have x11, x12 like this, x1n, x21, x22, x2n, like this we have a matrix, right? Let's say there are m data points, xm1, xm2, xmn. This is the matrix. This is the matrix which we are denoting as X. And W is basically the vector of W0 till Wn. Z here is the vector of the small z's. This was a small z, let's say this is a capital Z. Okay, so this is the equation. Now, let's say we are trying to find out y hat. Y hat is equal to sigmoid of Z, sigmoid function of Z. Sigmoid means what? 1 by 1 plus e to the power minus Z. A matrix of this is the y hat, right? Now we are coming to the cost function, friends. We'll be denoting y as a. Okay. Now j is equal to minus 1 by n y, big Y representing all the y values, that is y1, y2, y3 till ym, right? This is y. Y into natural log of a, or y hat. Y hat here is a. Okay. Okay, let me write y hat only. Plus 1 minus y natural log of 1 minus y hat. This is our cost function equation, this time in matrix form. And our condition remains the same. Let's say del j del w has to be equal to 0. Right, this is our minimization condition. Now can we derive this one here, friends? We can. Let's say we want to do del j. This can be rewritten as del y hat by del wi into del j del y hat. This can again be rewritten as del z del wi into del y hat del z into del j del y. Y hat. Now we strive to find out each of them step by step. First we find out del j del y hat, what that stands for. Del j del y hat is equal to del y hat of minus 1 by m multiplied by y log of y hat plus 1 minus y log of 1 minus y hat. Log means natural log in both cases. Now we take the constant out. Minus 1 by m del y hat of y natural log of y natural log of y hat plus 1 minus y natural log of 1 minus y hat. This is equal to minus 1 by m. First we differentiate this expression. This becomes del y hat of y is 0. Therefore one of the expressions goes out. The other expression remains, which is y into del y hat of natural log of y. The other expression becomes 0 because del y of del y hat is 0 plus 1 minus y del y hat of ln, that is natural log of 1 minus y hat. This is the only expression left, because if you differentiate this with del y, which is the other expression, that becomes irrelevant, that becomes 0, because 1 is constant and y is also with respect partial differential with respect to y hat gives nothing. It behaves like a constant. So this entire expression partially differentiated by y hat del y hat is 0. So these are the two expressions that we have left with. This is equal to minus 1 by m y by y hat plus 1 minus y by 1 minus y hat into minus 1. How does it come, friends? As usual, friends, let us understand it. Del y hat of natural log of 1 minus y hat is equal to, like we have decomposed things here, that's how we decompose this also, is equal to del 1 minus y hat of natural log of 1 minus y hat multiplied by del y hat of 1 minus y hat. This is how this del 1 minus y hat and this del 1 minus y hat cancel out basically. That's how the decomposition happens. Now this expression becomes 1 by 1 minus y hat. This expression becomes minus 1 because del 1 of del y hat is 0 and del minus y hat of del y hat is minus 1. So this becomes minus 1. That's how we get this expression. So we close the parenthesis. This, if simplified further, friends, becomes minus 1 by m y by y hat minus 1 minus y by 1 minus y hat. This expression. We simplify further, friends. This is equal to minus 1 by m y hat 1 minus y hat. This multiplied by y, this becomes y minus y hat minus y hat plus y hat. So this and this cancel each other. We are left with minus 1 by m multiplied by y minus y hat divided by y hat into y minus 1 minus y hat. If we take the minus sign inside, this becomes y hat minus y by y hat into 1 minus y hat. We have taken the minus sign beside 1 by m inside. So this has reversed. This has reversed to this. Now number 2, we go for the deduction of del y hat del z. This is equal to del z del z e to the power z by 1 plus e to the power z. This is how it works. This is equal to 1 by 1 plus e to the power z. This we keep constant in the first of the terms. Del e to the power z del z. And the second term is e to the power z remains constant. We do del z of 1 by 1 plus e to the power z. This one turns to e to the power z del z is e to the power z only. So this is e to the power z by 1 plus e to the power z plus this becomes e to the power z into minus 1 by 1 plus e to the power z whole square. This is the first term multiplied by, basically what we have done is we have taken 1 plus e to the power z as the differential in the first term. Then we will differentiate 1 plus e to the power z with respect to dz. That will become 1 takes common. This will become e to the power z. So the entire expression becomes e to the power z by 1 plus e to the power z minus e to the power 2z by 1 plus e to the power z whole square. If you simplify this one, this comes to be 1 plus e to the power z whole square. Above on the numerator, it happens to be e to the power z plus e to the power 2z minus e to the power 2z. These two cancel each other. We have e to the power z by 1 plus e to the power z whole square. Now curiously we can represent this expression we can curiously represent in terms of y hat only. How? Let's see. e to the power z by 1 plus e to the power z whole square, this can be written as e to the power z by 1 plus e to the power z, and the other expression is 1 by 1 plus e to the power z. Now incidentally this is 1 minus y hat, this is y hat, we have done in our previous deductions. So we just write that y hat multiplied by 1 minus y hat. This is our expression for del y hat del z. So the second expression is also derived. Now we go for the third expression, which is del z del wi. Now instead of wi, what we do is we write w only, because this we take as capital Z. This is a matrix form. Here also we do del w. So this becomes, if you differentiate z with respect to w, what you are left with is basically x. You are left with x, the matrix of x. Now we have all the three expressions. So now we write del j del w is equal to x multiplied by y hat into 1 minus y hat multiplied by 1 by m 1 by m y hat minus y hat minus y divided by y hat into 1 minus y hat. Now this expression and this expression cancel each other. So you have left with you del j del w is equal to 1 by m multiplied by y hat minus y into x. These are matrix forms. And you can see, friends, this is identically same as the form that we derived in case of our linear regression. Even in matrix form, we are getting the same derivation for our del j del w. That's about it, friends, for this chapter. We have learned the implications for cost function with respect to linear regression and logistic regression, both in terms of simple regressions and matrix form regressions. I would want to go deeper into different algorithms, their underlying mathematics and practical coding in the future chapters. The next chapter is polynomial regression. I want to see you there. If you find these videos valuable, please do subscribe to the channel. Do like the videos and share your feedback through comments. And also consider sharing it with your friends who might help from these videos. Thank you for being with me in this video. And until then, see you next time.